Hello students and my dear GATE aspirants. Welcome to this video pertaining to the very quick revision of heat transfer subject, which is a very important subject for the upcoming GATE 2025 examination, which is scheduled exactly 8 days from today, and that is on the 2nd February. So this subject is a very important subject for the mechanical GATE paper because its average weightage is approximately between 8 marks to maybe more than 10 marks. In GATE 2022, he has asked more than 11 marks from this subject. In fact, this is Sekhar from Msigma Gokulam. I have trained so many thousands of students who are preparing for the GATE examination in the last 30 years of my teaching experience for the GATE and IES. This subject, you have to pay extra attention in this 8 days of preparation. Okay, in the last 8 days of preparation, I am going to give very quick revision and some important tips how to attack a heat transfer problem for the GATE 2025 examination. And let us go into the subject, very quick revision of the subject. As you know, that subject contains majorly four topics: conduction, convection, radiation and heat exchangers. And out of these 4 chapters, generally most of the students feel tougher radiation and convection, but conduction is a little bit bigger chapter. Though students feel tougher convection and radiation a bit tougher, but actually they both those two topics are also very easy if you understand the fundamental concepts. First, let me start with the conduction. What are the very important topics that most likely to be asked in the GATE examination, which were asked earlier and again will be asked in the upcoming GATE examination. Coming to the conduction, the most important topics generally may be asked will be the composite slab, which is subjected to the convection on both sides. There may be hot gases and there may be colder ambient air, colder ambient fluid, and the temperatures may be given like this. And there is a convection heat transfer happening here, there is a conduction through this, there is a conduction and again convection. Okay, how to construct the thermal circuit? Construction of the thermal circuit is the core essence of this conduction heat transfer problems. Okay, and mind that you can construct the thermal circuit, you can draw the thermal circuit only if there is no heat generation in the slab. Later, after some time, I will consider the heat generation. Whenever there is a heat generation inside the slab or inside any cylinder or a sphere, you would not be able to draw the thermal circuit. You are not supposed to draw that. Here, there is no internal heat generation. Conditions are steady and constant thermal conductivities of the materials. We have the convection conditions imposed on both sides of the slab because H is a convection heat transfer coefficient having the units of watt per meter square Kelvin. You will be given conductivities and you will definitely be given the convection heat transfer coefficients, and you will be given the dimensions of the slab also, B1, B2. Okay, so that when you draw the thermal circuit here between the Tg and T infinity, this is the direction of the heat transfer. This is the direction of the heat transfer between Tg and T infinity. There are 4 thermal resistances connected in series. There are 4 thermal resistances connected in series. This is Tg, this is T infinity. The first resistance will be conduction, that is B1 by, first resistance will be convection, that is left hand side here. This is 1 upon H1A. Then we have the conduction B1 by K1A, B2 by K2A and 1 upon H2A, that is the convection resistance on the right side. But what might be asked in the GATE exam, if you just ask me, and you may be likely to be asked what is the intermediate temperature. Say for example, if this is T1, this is T2 and this is T3, you may be asked to calculate what is T2, or you may be asked to calculate what is the heat flux. Heat flux means heat transfer rate per unit area. Flux is the word used only in this subject. Heat transfer rate per unit area is called as the flux. In such case, area can be taken as 1 meter square. Okay, so you may be asked to calculate what is the T2 temperature. These terminals are T1, T2, T3. So this is a very typical kind of the problem most probably asked in the conduction. Sometimes Sometimes he may be given like this, only a single slab subjected to the convection on the right side. This is the convection. There may be a flux may be given, and K thermal conductivity will be definitely given. No thermophysical properties you need to remember. All the thermophysical properties like density, specific heat, conductivity and viscosity will definitely be given in the data of the problem. Nothing to remember regarding the conductivities. Okay, and there may be heat flux may be given. Okay, this temperature may be given. You are required to calculate what may be this temperature T2 given the T infinity. That T infinity is a symbol, usually we use it for the fluid temperature. So this kind of a general remember the thermal circuit, how to construct a thermal circuit and how to calculate the unknown temperature. Coming to the next next thermal. Actually, when you come to the conduction chapter, there are 4 thermal resistances which we need to remember. This is for the slab, this is for the cylinder, log R2 by R1 divided by 2 pi KL, and this is for the sphere, R2 minus R1 divided by 4 pi K R1 R2. Okay, this is for the cylinder, this is for the hollow cylinder. This is R1 is the inner radius, R2 is the outer radius, and K is the thermal conductivity of the material, and L is the length of the cylinder. V by Ka is for the slab. This is for the hollow cylinder. This is for the hollow sphere, hollow spherical container. This is one of the gate question he has asked. What is the thermal resistance formula? Thermal resistance formula for the hollow sphere. This is for the cylinder. This is for the cylinder. Please remember the 3 thermal resistance formula. You would be able to construct the thermal circuit only when you remember all these 3 resistances. Or otherwise, you may ask in one of the gate examination, he has asked that that there is one hollow cylinder, a bare cylinder, some convection situation is happening here. This temperature may be given T1 and this temperature is given. This temperature may not be given. Actually, sometimes we need to calculate that. So, how many resistances will be existing between T1 and T infinity? For this radial heat transfer, this is a radial heat transfer. When you come to the hollow cylinder cases and hollow spherical container cases, it will be a radial heat transfer. In case of these slabs, it is not radial, it is along the x direction. If this is x direction, along the x axis, because most of the gate problems will be asked only one-dimensional conduction. Two-dimensional conduction only one time he has asked, that is in gate 2016. But for that, in all these 25 to 30 years of gate papers, if you see, only the one-dimensional conduction we consider. That one-dimensional, in case of the slabs, it is along the x direction. In case of the cylinders, it is along the radial direction. Okay, this is a radial conduction heat transfer taking place. Radial conduction and convection. Whenever H is given, whenever the H is given in the problem, think that yes, there are convection conditions are prevailing. So between T1 and T infinity, for this radial heat transfer, how many resistances you may expect? 2 resistances. One is conduction and then by convection. So how many thermal resistances will be there between T1 and T infinity? See, when you construct the thermal circuit, between what terminals we are putting the thermal circuit, we have to keep in mind. Between T1, that is the inner surface temperature of the hollow cylinder, and the ambient fluid, there are 2 resistances. One is conduction resistance offered by the hollow cylinder. Other thing is the outside convection resistance. Remember that conduction is always identified or notified by the K, whereas the convection is always notified by the H. If H is given, yes, there is a convection. If the K is given, there is a conduction happening. There are 2 thermal resistances in series. So what is the first resistance? Ln R2 by R1 divided by 2 pi KL, where K is the thermal conductivity of the material. By the way, I would like to tell you that In many of the gate examinations, he is asking you to arrange they will give you the 4 materials. He will arrange you either the ascending order or descending order of the thermal conductivity. As you all know, metals are the very good conductors, whereas the gases are the very poor conductors or very good insulators. There are some solid insulators also, like rock wool, refractory brick, glass wool, etc. Okay, asbestos, etc. They are all the insulating materials, solid. Even the gases have got the very low thermal conductivity. Gases also conduct the heat, but with a very low thermal conductivity. They may ask you, they may give you 4 different mediums, 4 different materials. Some of them may be gases or the solids and liquids like that. Liquids definitely possess a better conductors than the gases. For example, thermal conductivity of water, it will be around 0.62 or 0.63, changes with temperature. For the air, it will be around 0.026 watt per meter Kelvin. So gases are the least heat conductors, and better metals are the best heat conductors. Of course, there are certain crystalline materials, pure crystalline materials like diamond, which has got the highest thermal conductivity. They may ask you to arrange the thermal conductivity materials in ascending. We are not supposed to remember the values of K, but we are supposed to arrange the K values, ascending or descending order. Because many times it was asked in the gate. And then when you come to the convection resistance, 1 upon HA. And when you talk about the convection resistance, because earlier thing I had given as the 3 resistances, all are conduction resistances. Apart from this conduction resistance, was general convection resistance, general thermal resistance, convection thermal resistance will be 1 upon HA. Because what is A? A is the area of contact. Area of contact between the solid and the fluid. Because after all, whenever you talk about the convection, what law that governs the convection? Newton's law of cooling. The rate of heat transfer by convection is equal to Q is equal to HA delta T. A is the area of contact, area of touch, area of exposure between the solid and the fluid. Okay, so when you come to this, when you come to the thermal resistance here, what is the area of contact between the outer surface of the cylinder and the air? Maybe outside fluid, maybe air or water, 1 over 2 pi R2L. So this kind of a problems will most likely to be asked. This is a radial heat transfer given as what Q watts, but never try to calculate flux here. The main difference between the slab case and this radial heat transfer is, here the area of heat transfer is constant. In case of the slabs, area of heat transfer is constant, but here the area of heat transfer is not constant in case of the radial heat transfer. Okay, supposing if you take the just a spherical thing, a hollow spherical composite sphere, R1, R2, R3, it is a composite sphere having a different thermal conductivities, K1 and this is K2. The radial heat transfer is happening between the innermost surface, the T1 and say T3. How many resistances you may expect between T1 and T3? There will be 2 resistances. One is conduction resistance offered by the inner sphere, and the other is a conduction resistance offered by the outer sphere. This is a sphere. If it is a hollow composite sphere, how to construct the thermal resistance? R2 minus R1 by 4 pi K R1 R2, R3 minus R2 divided by 4 pi, this is K1, this is 4 pi K2, R2 R3. This is for the hollow composite sphere. Maybe this is a one sphere, it is lagged with some kind of an insulation. Lagging means keeping. An insulation may be lagged around the hollow sphere. If you want to construct the thermal circuit, this is the way. This is a thermal circuit for the composite sphere, composite spherical container. Composite means more than one material. Composite slab means a slab made up of more than one material. Composite cylinder means more than one material. Okay, one lagged over the other. So all these circuits are the series circuit only. Rarely you may have the parallel, but that may be only one gate. I think gate 2024 he has asked there. This is this is a parallel circuit. If the materials are A, B and C, we need to construct the series parallel network. This is the resistance offered by the material B. This is the resistance offered by the material C. This is, but the area of heat transfer, one must be careful. See, when you talk about the thermal resistance of the conduction B by Ka, B is the thickness of the slab. What is that A? Area perpendicular to the direction of heat transfer. If this is the direction of heat transfer, what is the conduction area for the B? This is only this part. What is the conduction area for C? This is AC. What is the conduction area for the A? That whole AB plus AC, conduction area for the area will be AB plus AC. This depth may be taken as 1 meter, but generally this is the situation, that is a parallel because heat conduction happening parallelly through the two materials B and C. These two are in parallel in connect and then connected in series with the A. So this is the thermal circuit. Supposing if this is T1 and this is T2, this may be parallel series network. Yes, this is one particular important thing regarding the conduction. Coming to the another important topic, which is called as the critical radius of insulation. Very important topic. Very commonly the questions are asked in this. Very frequently the questions are asked. What is the concept of the critical radius? For thin wires, for sufficiently thin wires, if you lag the insulation around that, if you keep the insulation around the wire, this is the wire, this is the insulation, solid wire this is. If you lag the insulation around the solid wire, if the wire is thin, there may be increase of heat transfer rate instead of decreasing it. That is a very important concept. For thin wires, for sufficiently thin wires, for small radius wires, if you lag the insulation, if you keep the insulation around it, it may result in the increase of heat transfer rate instead of decreasing it. So that is the formula given by our critical radius of insulation is given by K by H. If the radius of the wire is lesser than the critical radius of insulation, then there is increase of heat transfer rate instead of decreasing. If this is RO, this is the critical radius value, K by H. If the radius of the wire what you initially consider, is lesser than this critical radius of insulation, if you put up the insulation around the wire, it will result in increase of heat transfer rate. That is the main concept. I repeat once again, if the radius of the wire what you initially consider is lesser than the critical radius of insulation given by this formula K by H, where K is the thermal conductivity of the insulation, not the wire, and H is the outside convection heat transfer coefficient. So if the H is a outside convection heat transfer coefficient, if the radius of the wire what you initially consider is lesser than the critical radius of insulation, if you put up the insulation around the wire, it will result in increase of heat transfer rate. So whenever you are attempting the critical radius problem, my suggestion is first calculate the critical radius by using that formula K by H, where K is the conductivity of the insulation given in watt per meter Kelvin and H is the outside convection coefficient. Then immediately draw the graph. Okay, put all the dimensions are given in the problem in this graph. So definitely you will be given what is the radius of the wire. You will be given the radius of the wire will be given. So mark that critical radius value and what is the radius of the wire. You just check it whether you are beginning the journey on the left hand side or on the right side. Supposing if the radius of the wire considered is already more than the critical radius of insulation, if you put the insulation around it, it will result in decrease of heat transfer rate, because when you provide the critical radius of insulation, heat transfer rate will be maximum. So you should attempt in a proper manner before attempting the problem on critical radius. First calculate the critical radius value, draw the graph, put all the values in the graph and then start what is being asked in the examination. You can easily identify that critical radius problem. Generally you can identify like this. Most of that critical radius problems, you will read that the radius of the wire will be very small, maybe few mm, 2 mm or 3 mm or maybe around 1 cm, less than 1 centimeter. Just by seeing that data itself, you can suspect that the problem is on critical radius of insulation. Just keep that in mind. This is for the cylinder. This is for the cylinder. Same concept you can apply for the sphere also, but there the formula is different. 2K by H. This formula is for the sphere, spherical. So concept of critical radius is applicable both for the cylinder and for the sphere. The main concept is, if the radius of the wire or the sphere considered is lesser than the critical radius of insulation, if you wrap the insulation around it, it will result in increase of heat transfer rate. You can see the graph there, okay. If you begin the journey here, if you put the insulation, you will see that increase of heat transfer rate. If you begin the journey here, supposing if you put the insulation, begin the journey on the right hand side of the graph, and you will see that heat transfer rate will be decreasing, okay. So please remember, this is a very important topic that may be asked. Then coming to the generalized conduction equation, the three-dimensional generalized conduction equation you have to remember is a most generalized conduction equation where you consider the heat generation in the slab and steady or unsteady. In all the previous problems, in all the previous discussions I have done, we have made one most common assumptions like steady state heat transfer, one-dimensional heat transfer, and thermal conductivity is constant. Some assumptions we have made. So now all those assumptions were deleted except one assumption, that thermal conductivity and thermophysical properties of the material are constant. This alpha is called as the thermal diffusivity. Very important thermophysical property of the material in meter square per second, its units. It is defined as K by rho Cp, thermal conductivity divided by thermal capacity. That is the definition of thermal diffusivity. This is the generalized conduction equation. This is the most generalized heat conduction equation. Only one assumption I have done, that all the thermophysical properties like thermal conductivity, density, specific heat, all are constant, okay. In the entire subject, we deal with only 4 thermophysical properties, K, rho, Cp, and if it is a fluid, mu, viscosity. But for that, no other things will be there. But the K by rho Cp is called as the another property called as the alpha. Later I am going to put up in convection, there is one dimensionless number called as the Prandtl number, which is also a thermophysical property of the fluid. Prandtl number will be there only for the fluid, not for the solids, okay. That is also a property. So these are the generally properties which will be given in the any heat transfer problem. Okay, this is a generalized conduction. For a steady state, supposing if it is a two-dimensional, if it is only one-dimensional and heat generation, if it is a steady state, this is a time. The t means, small t means time. This will be there only in the unsteady state. If it is a steady state, dou t by dou t will become 0. This will become 0 only. If it is a one-dimensional, only temperature is only a function of x. Temperature dou t square t by dou y square and dou square t by dou z square becomes 0. Okay, Q dot, what is this Q dot? Rate of heat generation per unit volume. That is a uniform rate of heat generation per unit volume. Heat generation rate. Please remember this symbol, I give it for the heat generation rate per unit volume. So please remember this equation. K is the thermal conductivity of the material. And this heat generation case also very often things were being asked in the many gate examinations there. So heat generation cases, please give an extra attention. Heat generation in slabs. Actually, heat generation you may ask in slab or a cylinder, but until now it was never asked in the sphere. There may be heat generation in the sphere also, but most likely they may be asked in the heat generation inside a slab. Supposing there is a slab where heat is being generated uniformly. I already said, don't try to construct the thermal circuit. Whenever there is a heat generation, we should not and we cannot construct the thermal circuit. A thermal circuit you can construct only if there is no heat generation inside the body. This is a uniform heat generation is given, and left hand, right hand side temperatures may be different or maybe sometimes they may be equal. and where you this is the x direction, maybe x is chosen here, or sometimes x may be chosen at the mid plane. So this is one important thing that we need to revise very quickly. And we have to begin the problem by taking the generalized conduction equation, assuming that steady state and one dimensional. I already said temperature is assumed only as a function of x, okay, not a function of y, not a function of z. By integrating this equation, dou T by dou x is equal to minus q dot by k into x plus c1, and again integrating minus q dot by k into x square by 2 plus c1x plus c2, okay. By integrating that equation, you will be getting the two constants of integration that are to be calculated from the two given boundary conditions. You will be given both sides the temperatures of the slab, and the two constants can be obtained, C1, C2 are the constants of integration, can be obtained from the two boundary conditions. At x is equal to 0, we know the temperature, at x is equal to L, we know the temperature T2. Okay, so from that C1, C2 can be calculated. And what may be asked in the heat generation cases? Mostly the question will be asked like this: whenever there is a heat generation inside a slab, or it may be inside a cylinder, or maybe inside a sphere, how much will be the maximum temperature, and where would you see that maximum temperature? At what x? Measured from the left face, you may be seeing the maximum temperature in the slab. Okay, and how much is that maximum temperature in the slab? That is the question. Most likely will be asked in GATE 2022, I guess. He has asked again he has slightly confused the problem. He has given a slab. And mid plane will be there. He has given, slightly changed the problem. He has given both the temperatures, but in that problem what he has given is, and thermal conductivity is a function of temperature. He has given. Actually 99% problems of heat transfer, we assume that thermal conductivity is a constant. But in that particular problem, he has given a heat generation. There is heat generation. See how he has combined the things. Most of the heat generation problems given in GATE, we assume that K is constant. But in that particular problem, he has given that thermal conductivity is a variable dependent on the temperature. Some C is a known constant there. C value is a known constant, T is the temperature, this is the thermal conductivity. Okay, this function was given and we are required to calculate where is the maximum temperature and how much is that maximum temperature. This is the problem given in GATE 2022. So it's slightly twisted. But now we have to take that generalized conduction equation, okay, dou T by dou square T by dou x square. But there, before that, K is, you have to thoroughly remember the derivation of that equation, generalized conduction equation with a variable thermal conductivity. Now K is a function of temperature. So keeping that K because while writing this equation, dou square T by dou x square plus Q dot by K is equal to 0, this is not applicable now. Because this is the equation we have used when if K is assumed as constant. But now K is not a constant, K is a function of T. So we have to take a one step before that in the derivation and begin that, write that equation and keep integrating that by using this function, and then we will be able to get the constants of integration. Because all our differential equations, generalized conduction equation is a second order equation. Obviously, because it is a second order differential equation, you will get the two constants of integration that are to be calculated from the given boundary conditions. But while integrating, you have to be extra careful. In this special case, where thermal conductivity is a function of temperature, we have to begin the integration not with this, not because this is not applicable here. This is applicable only if steady state, one dimensional, thermal conductivity is constant. But if the conductivity is a variable, then we have to begin the integration slightly considering a step just before that, because you have to remember the derivation of the generalized heat conduction equation. Okay, so this is, remember, give an extra attention for the heat generation case. I will give a different chances of the heat generation. Supposing there is one thing I would like to tell you here. If there is a uniform heat generation, if both sides the temperatures are same, then by default you will see the symmetric parabolic temperature. You will see the maximum temperature at the mid plane. This is the symmetric parabola. Symmetric parabola. Whenever there is a heat generation is there, what is the temperature distribution? Parabolic temperature distribution. Supposing in the slab, if the left hand side temperature is more than the right hand side temperature T1, T2, here also parabolic but with the maximum temperature you will see in the left half. In the left half you see, okay, if this is the mid plane, this is the mid plane, this is the mid, in the left half you see the maximum temperature. Why? Because if T1 is greater than T2. On the other hand, if T1 is lesser than T2, so for example, this is T1, this is T2. If T2 is greater than T1, you will see the maximum temperature, you will see the maximum temperature on the right hand side of this slab. Okay, this option may be possible. If both sides the temperatures are same, then you will see the maximum temperature at the mid plane. So any option is possible. Any option is possible, okay. And suppose that if one side of the slab is completely insulated, say for example this side of the slab is completely insulated, say, then the temperature profile will be parabolic with the maximum temperature at the insulated surface. This is insulated and there is a heat generation inside the slab. Whenever there is a heat generation, Q dot symbol is given, you will be clearly mentioned that it is in watt per meter cube, uniform heat generation, okay. It is a uniform heat generation. But one thing is certain, whenever there is, you are doing a problems with heat generation, keep the most important energy balance equation in the mind. Whenever there is a heat generation inside the body, to maintain the steady state, all the heat generation in the entire control volume must be given to the surrounding fluid to maintain steady state. I repeat once again, whenever there is a heat generation inside a body, inside a system, inside a control volume, to maintain the steady state conditions, steady state means what? Temperature do not change with time. To maintain the steady state conditions, all the heat generated in the entire body must be convected to the surrounding fluid, either from one side, in this case there is only convection from one side, or from both sides. Suppose if it is not insulated, heat may be convected from this side also. Then only you can maintain the steady state conditions. So for example, for this slab, you want to write the energy balance. Supposing if you want to write the energy balance for steady state. Steady state means temperature will not change with the time. Energy balance for steady state. If you write heat generated, total heat generated in entire slab, total heat generated in entire slab should be equal to heat convected to fluid. Whenever there is a convection is there, automatically it will be identified by H. H speaks of convection just like K speaks of the conduction. Okay, convection to the fluid. Whenever there is a convection, what is that law we refer? Newton's law of cooling. Whenever there is a conduction, what is that law you refer? Fourier law. Fourier law for conduction, just like Newton's law of cooling is for the convection. So what is the energy balance equation for this situation for steady state? For steady state, steady state means what? Temperature is not a function of time. Almost throughout the subject we assume steady state, except in only one particular topic in conduction called as the lumped heat analysis. Except that, throughout the subject we assume that conditions are steady. Temperature at a particular spot will not change with respect to the time. So this is how to calculate heat generated. Q dot into volume of slab is equal to HA. Say for example, this temperature is HA T2. This may be T1. T2 minus T. So this is energy balance. A is the area of this slab. What area into length will be the volume. So we can calculate anything, any temperature T2. When one T infinity may be given, you can calculate T2. Or if you are given the, what is the volume of this slab? Length into area. Okay. You will see the maximum temperature only at the insulated surface. Supposing in the previous cases, say for example here, in the previous cases, total heat generated, half will be convected from the right side, half will be convected from the left side. But in all these cases, mind that there is always a convection happening. What for? What for this convection is happening? To maintain the steady state. Here also, there is a convection here from the left face, there is a convection here from the right face. So in all these diagrams, I can say to maintain the steady state, the total heat generated in the entire slab should be equal to the heat convected. There is a heat convected, there is a convection happening here, there is a convection, equal amounts of convection. Total heat generated 50% here, 50% here. That is why you see the maximum temperature at the center line or at the mid plane. Here there is a convection, unequal convections, but definitely I can say energy balance that total heat generated in the entire slab should be equal to the heat convected from the left face plus heat convected from the right face. So this problem once again is asked in a, I think gate 2021 I guess, but he has asked in a different manner. What he has asked is, he has given 3 slabs. But heat generation is there only in the central part. There is no heat generation here, no heat generation here. But there is a fluid given. Convection happening from the left face and there is a convection happening from the right face. Convection to fluid. Whenever there is a convection, by default H1, H will be there. Okay. You speak of convection, H will be there. You speak of conduction, K will be there. So how to write the heat generation only in the central slab? Here no heat generation. Here no heat generation. Here also no heat generation. So how to solve the problem? So I think he has asked what is the right side temperature. You will be given the left side temperature. He will ask you to calculate the right side temperature. How to write the energy balance for steady state for the entire system, for the entire control volume? How to write the energy balance? Total heat generated in the entire slab, in the entire system, which is equal to the total heat generated in the central slab only, because only this is generating heat. It should be equal to the heat convected from this side plus heat convected from this side. Then only the whole system will be in a steady state. For the steady state conditions of the entire control volume, the heat generated in the central part, this central slab, should be equal to the heat convected from the left side fluid to the plus heat convected to the right side fluid. Total heat generated here is equal to heat convected this side plus heat generated from the right side. When you write the convection, obviously Newton's law we have to write HA. This is area. Of course, that area will get cancelled throughout because this conduction area and this convection areas are same here. Slab in the case of the slabs, area of heat transfer is same on both sides. So total heat generated here should be equal to the heat convected from this side. Or when you talk about a convection, what is the convection heat transfer here? H area into delta T. This temperature may be T1. If T1 may be given, if you can calculate T2. If T2 is given, you can calculate T1. So when you talk about the heat generation problems, just keep in mind how to write the energy balance for steady state. Things may be asked sometimes in one of the gate examination, heat generation inside a cylinder. There is a fluid, T infinity referring to the fluid. Where would you see the maximum temperature? By default at the center line axis. In case of the cylinder, by default, it is at the axis, maximum temperature. And what will be the temperature distribution? Temperature distribution again will be parabolic with the maximum temperature at the axis. Maximum T naught or T max, both mean the same. Sometimes T naught they call, or T naught or T max, maximum temperature you would see at the center line. Temperature distribution is axis symmetric parabola. The temperature distribution is axis symmetric parabola. So we can write this, you can remember T naught minus TW is equal to Q dot R square by 4K, where R is the radius. TW is the peripheral temperature. How to calculate the peripheral temperature? Again the energy balance. What is the energy balance for steady state? Total heat generated. What is the total heat generated? Q dot into volume of the cylinder, because Q dot is always, whenever you are given a heat generation in the gate problem, Q dot is always given in watt per meter cube. Heat generation per unit volume into volume of the cylinder is equal to H into what is the convection area? Convection area is always the contact area. Convection area is always the contact area. So this from which we can calculate the TW, the surface temperature of the wire. What is the convection area? Because where is the convection happening? Convection happening from the surface. What is the convection area here? Pi d or 2 pi r into length. Convection area is nothing but a contact area between the solid and the fluid. So this is the convection area. This is convection area, contact area. Newton's law of cooling always says that HA delta D. What is that A? Q is equal to HA delta D. What is that A? Area of convection, area of contact, area of touch between the body and the fluid. So from which you can calculate the peripheral temperature, TW. And I can use this, we can get the maximum. Once you get the peripheral temperature, what is the T naught? T naught is the maximum temperature. What is the temperature distribution? Axisymmetric parabola. If it is a sphere, if it is Q dot R square by 6K. If it is a sphere, it will be Q dot R square by 6K. That is the main difference. So remember, give extra attention in the conduction chapter, more attention to the heat generation problems. Very often it is being asked. So in the conduction chapter, I can say there are 3 topics we have to give extra focus in this last 8 days of preparation. One is heat generation. Second thing is the critical radius of insulation. That is very easy. And the third thing is that now I am going to do lumped heat analysis or unsteady state conduction. Actually, there are some topics, fins are also very rarely being asked. In GATE 2021 he has asked, and again GATE 2010 he has, only 2 times he has asked about the fins. Fins are not that important, but I will do that. But most importantly, more important topic than the fins in conduction chapter is a lumped heat analysis or unsteady state conduction, where we define the most important dimensionless number called as the Biot number. Questions on Biot number are very common in GATE. When you come to the unsteady state or transient, this is also called as the unsteady state or transient. Transient means temperature may change, transient conduction. Now here the temperature may be a function of, temperature may be a function of space, temperature may be a function of time. Temperature may be a function of time. So where we talk about mostly the lumped heat analysis, the n number of times, so many times the lumped heat analysis problems were being asked, so many times, and many we can see in 17, 2000. What is lumped heat analysis and what to calculate? Generally, you will be given a spherical body or a cylindrical body like this. Say for example, a hot body which is at an initial temperature of Ti, I means initial. It is suddenly exposed to a cold fluid. T infinity is symbol refer to the fluid. There is a convection happening, convection referred by H. So what we are being asked is, say initially this Ti will be given, the size of the body will be given, H will be given, fluid temperature will be given. After exposing the body suddenly to the fluid, after 1 minute of time, what will be the temperature? Or to reach so and so temperature, how much time may be taken? Because this may be given, you may be asked to calculate this, or this may be given, you may be asked to calculate the temperature. So only one lumped heat analysis. What is the criteria? Biot number should be less than 0.1. What is Biot number definition? They may ask this. Hs by K, where S is the volume of the body divided by surface area. Generally, S will be equal to the R by 3 for spherical body. S is R by 3. For plate, S is equal to L by 2. For thin plates, for thin plates, where L is the dimension of the plate, L by 2 is the characteristic dimension. Okay. For cylindrical also, long cylinder also, it will be half of the radius. So maybe cylindrical body or a plate, usually you will be given mostly for the spherical body. So you will need to calculate the temperature at any instant of time. Only one formula is there, Ti minus T infinity divided by T minus T infinity is equal to e to the power of HA by rho V Cp into time. So this is the only formula we have to remember. When this formula will be applicable? Only as long as the Biot number is less than 0.1. Biot number is the criteria whether lumped heat analysis is valid or not. What do you mean by lumped heat analysis? What do you mean by that? Lumped heat analysis means the temperature of the body is uniform throughout the body at any instant of time. At any instant of time, if you see the temperature of the body at the core of the body and at the periphery of the body, they will be exactly equal. Even if there are temperature gradients, they are negligibly small. That means internal temperature gradients, internal temperature differences, if anything they are negligibly small, too small. Internal temperature gradients are very small. That means core of the body and periphery of the body, core of the body and periphery of the body are almost same at any instant of time. Body temperature decreasing with time, but not, you don't see any temperature differences within the body. So that is called as the lumped heat analysis. The criteria is Biot number given by this formula. Actually, Biot number definition also they was asked in Biot number is equal to internal conductive resistance, ICR they call, internal conductive resistance divided by external or surface, external convective resistance, ICR by ECR, abbreviated as ICR by ECR, for which as Biot number is given by Hs by K. If K is high, if K is very high, H is very small, size of the body is, S is, you can remember something like a size, because S is equal to R by 3 for the sphere, for small spheres, for thin plates, for very long rods, thin and long rods, the metal made up of metal. If the K is high, S is small, H is small, Biot number will be automatically lesser than 0.1. This is the criteria for lumped heat analysis. If it is more than 0.1, if the Biot number goes more than 0.1, what we do? We cannot write this formula for the lumped heat analysis. This formula, right? This formula we have to remember. This formula, give extra attention to this formula. Okay. This, in fact, this rho HA by rho VCP has got in units of per second. Therefore, if you reverse that, rho VCP by HA is called as the time constant. This rho VCP by this rho VCP by HA is called time constant of the body, because it has got the units of second. Time constant of body, it has got the units of second. This has got the units of second. That is why it is called time constant of the body. Supposing if the Biot number value becomes more than 0.1, can you write this formula? No, you cannot write this formula. Then how to solve the problem? Then we have to take the help of the Heisler charts. If Biot number is above greater than 0.1, implies Heisler charts must be used. In the Heisler charts, we see the two numbers. One is Biot number and Fourier number. So when you are in the transient conduction heat transfer, we get two dimensionless numbers. One is Biot number, that is Biot number is given as Hs by K. Another is a Fourier number, alpha into time by S square. Okay. So this alpha is called as, we know that this is the thermal diffusivity, T is the time. This Fourier number is also called as the dimensionless time. So in the Heisler charts, we come across two numbers. Heisler charts, always x-axis will be Fourier number. The typical Biot number, typical Heisler charts will be there like this. This is 1 upon Biot number, each line. This is a Fourier number. This is the temperature distribution, because when you are using the Heisler charts, temperature of the body will be different at the axis and will be different at the periphery. When you have to make use of the Heisler charts, when lumped heat analysis is not valid, which means you will see different temperatures at different locations within the body at a given instant of time. You will see different temperatures at different locations within the body at a given instant of time. That is called transient conduction heat transfer, where lumped heat analysis is not valid. Lumped heat analysis valid means what? At any instant of time throughout the body, you must observe the same temperature, uniform temperature. If the lumped heat analysis is not valid means you will see a different temperatures at the different locations at any given instant of time, for which the Biot number goes above 0.1. There we have to take the help of the Hassler charts, where we see the two numbers, Biot number and as well as the Fourier number, alpha T by S square. Alpha is the thermal diffusivity, T is the time. So Fourier number is also called as also known as dimensionless time. Okay. So two dimensionless numbers we get in conduction chapter. One is Biot number and other is the Fourier number. Yes. And so this is a very important. So until now the important topics I am giving as the critical radius of insulation, heat generation inside a slab, cylinder and sphere. There is a second. Third thing is the lumped heat analysis. So many times the questions were asked in these topics. And also the first topic, as I said, the composite slab, composite cylinder, and okay. And coming to the fins, and another thing, there fins whenever you are given a fins, just only two formula you have to remember. In every fin problem, unless it is mentioned, you always consider that tip is insulated. Unless it is mentioned, tip insulated case you consider. We will get the answer. Only two cases remember, actually a third case is there, but if two cases if you remember, you can do any fin problem. One is infinitely long fin, very long fin. Number two is finite in length is finite, but tip is insulated. We have to calculate we have to remember what is the heat transfer rate and what is the temperature distribution. Temperature is a function of x. What is this function and what is the heat transfer rate? Only two formula you have to remember. For this insulated tip case, it is given as square root of Hp Ka, P is the perimeter, T naught minus T infinity into tan HML, hyperbolic tan, so many watts. This is the heat transfer rate taking place from the fin to the fluid temperature. Standard notations you have to remember. T infinity is the fluid temperature, this is the base temperature, root temperature or base temperature. K is the thermal conductivity, A is the profile area, remember that. A is not the surface area, rather it is a profile area or the cross sectional area they call. M is given by root of Hp by Ka per meter. M is given by root of Hp by Ka per meter, where P is the perimeter, K is the conductivity and A is the cross sectional area. Yes, these are this case you remember. Supposing if it is an infinitely long fin, the formula will change. Sorry, there is one more formula I would like to give here. The temperature distribution, T minus T infinity by T naught minus T infinity is equal to cos HM L minus X divided by cos HML. Only these two formula remember. This is the formula for the temperature distribution. This is the formula for the heat transfer rate. Just two formula remember for the fin. And of course, there is one more thing, fin efficiency and fin effectiveness. When you talk about the fins, only heat transfer rate, temperature distribution, efficiency, fin efficiency formula and fin effectiveness definition and its formula. That's all. Nothing to remember. Just make a very simple notes while quickly revising that. M is the root of Hp by Ka. This is a hyperbolic cosine. This is a hyperbolic tan. Okay. For the very long fin, for infinitely long fin, very long fin, the temperature distribution is given by T minus T infinity divided by T naught minus T infinity is equal to e to the power of minus mx. X is always measured from the root. At the root x is equal to 0, at the tip x is equal to L. But these formulas are valid when the tip is insulated, fin tip is insulated. Actually, for any fin problem, if you assume that the tip is insulated, you will get the answer. But sometimes he may mention that fin is very long, infinitely long, use this. Then one more formula is there, that is heat transfer rate through the fin will be square root of Hp Ka into T naught minus T infinity. But this case is not that important. Only when he mentions infinitely long fin, use this. Otherwise, use the previous formula, but insulated tip case. And another thing is efficiency of the fin is given as tan HML by ml. But fin problems, I think 2 or 3 times only for the last 20 years of GATE, 25 years. I remember it's only twice. GATE 2010 years asked, I still remember, and 21 or 22 years asked only once. That's all, not more than that. And okay, one time he has asked the fin effectiveness as such. Fin effectiveness. What is the heat transfer definition for the fin efficiency of the fin? Heat transfer rate, actual heat transfer rate divided by Q actually taking place divided by maximum possible, how much how it can happen. Maximum possible means that is when fin material has infinite thermal conductivity. If the fin material has got infinite thermal conductivity, how much heat would be transferred from the fin to the fluid? That is the maximum possible heat transfer rate. And numerator is actually how much is taking place, because no fin material can have infinite thermal conductivity. Which material can have infinite? No material can have. If the fin material has got infinite conductivity, how much would have been the heat transfer rate? That is called as the how much heat, that is the maximum possible heat transfer rate. And another definition is the effectiveness of the fin. Q with fin, heat transfer rate with fin divided by Q without fin. Effectiveness of the fin will be Q with fin by, and fin only when the effectiveness of the fin is greater than 2 or 2.5, fins are worth keeping. Otherwise, we do not keep the fins at all. Effectiveness of the fin only when it is more than 2.5 or 2 or 2.5, we would go for using the fins. Otherwise, we will not keep the fins at all. And effectiveness of the fin is directly proportional to the 1 upon root h. That means when the h is very high, we will never use the fins. Epsilon is more for thin fins and good number of fins. Good number of fins. If the number of fins are more, and if it is a thin fin, very thin fin, then the effectiveness of the fin will be high. So these points, if you remember regarding the fin. So with this conduction is conduction revision I have done. So you broadly remember what to revise in conduction. As I said, composite slab case where it is subjected to convection on both sides. Okay, and then how to construct the thermal circuit for a composite slab, for a composite cylinder particularly, and then comes to the critical radius of insulation, then heat generation inside a slab, cylinder and sphere, then the generalized heat conduction equation. Actually, okay, what are the various parameters? What do you mean by steady state, unsteady state? Then we have the lumped heat analysis, particularly unsteady state, where we define Biot number and as well as the Fourier number. Then again the fins. Okay. So these are the broad important topics which you have to revise in the conduction. Coming to the radiation. Generally people fear of radiation. I don't know why, but I observed with all my 25 to 30 years of GATE teaching, generally people when they talk about radiation, how to solve the problems. Actually radiation is very easy if you remember the fundamental definitions like total hemispherical emissive power, emissivity, monochromatic emissive power of the black body, monochromatic emissivity. If you just remember these definitions, any problem we can do. We know that epsilon is E by EB. B is for the black body. Black body is a character of the black body. It has 3 characters. It is a perfect absorber. All the radiation falling on the black body completely absorbed, and a ideal emitter. As compared to any other black body, non-black body, as compared to any other non-black body emits more. That is why emissivity is always less than or equal to 1. Emissivity of the black body is 1. Emissivity compares. What is that E? Total emissive power. Total hemispherical emissive power. Total hemispherical emissive power having the units of watt per meter square. How much energy body emits, radiates per unit time, per unit area is called as how much radiation energy body emits. That is the total hemispherical emissive power. This is a monochromatic. When I give the lambda, it is a monochromatic. Okay, this is a monochromatic emissivity. When you talk about the gray body, for gray body, epsilon lambda, gray body means epsilon lambda is not a function of lambda. If the monochromatic emissivity is independent of the wavelength, such body is called as the gray body. Black body means perfect absorber, ideal emitter, and also one more thing is there, diffusive in nature. Black body has got three characters: perfect absorber, ideal emitter, and diffusive in nature. Okay, for gray body, monochromatic emissivity is independent of the wavelength lambda. So these definitions, and of course the three definitions alpha, rho, and tau. This is absorptivity. This is absorptivity. What do you define the absorptivity? The fraction of radiation energy absorbed by the body. The fraction of radiation energy incident upon a body which is absorbed by it. If 100 units are falling, 50 units body absorbs, absorptivity is 0.5. How much percentage, how much fraction of the radiation energy incident upon a body is absorbed? That is called as the alpha. This is reflectivity. Rho is reflectivity. Tau is transmissivity. Of course, for the opaque body which would not transmit any energy, tau will be 0. Tau is equal to 0 for opaque body. Opaque body means it will not transmit any energy, it will absorb and reflect. Therefore, alpha, generally for any body, alpha plus rho plus tau is equal to 1. For opaque body, alpha plus rho is equal to 1 for opaque body because tau is 0 for the opaque surface. Opaque means it would not transmit. A concrete slab is a opaque. A glass is there, window glass. Window glass is not opaque, it is a transparent body because energy can pass through that. Energy can enter and pass through that surface, that is called as a non-opaque body or a transparent. Okay. So you have to remember this, and above all, we have to remember all the laws. Kirchhoff's law. Kirchhoff's law of thermal radiation. Absorptivity is equal to emissivity. When the body is in thermal equilibrium with its surroundings, Kirchhoff's law of radiation states that whenever a body is in thermal equilibrium with its surroundings, its absorptivity is equal to its emissivity. Best example is black body. For black body, which is a perfect absorber, alpha of the black body, emissivity of the black body is 1. Okay, remember that. Second law is the Planck's law. Planck's law is very important because from this law another subsidiary laws comes, Wein's displacement law, etc. Stefan Boltzmann law, they are derived from the Planck's law only. Planck's law is EB lambda is equal to 2 pi C1 into lambda divided by lambda to the power of 5 into e to the power of C2 by lambda t minus 1. The monochromatic emissive power of the black body depends upon the temperature and as well as the wavelength. That is the one as such. This one. So the C1, C2 are constants. Okay. The monochromatic emissive power of the black body is dependent upon the absolute temperature of the black body and its wavelength of emission. Because thermal radiation on the electromagnetic spectrum, thermal radiation occupies a bandwidth of 0.1 to the 100 microns. So this EB lambda is a function of lambda at a given temperature of the body. The black body will emit different amounts of monochromatic emissive powers at different wavelengths. Best example is sun. For example, if you plot this for the sun, if the Planck's law, if it is plotted, it is asked once in GATE. This graph is asked once in GATE. I still remember, I think it is a GATE 2005 is asked. At 3 different temperatures, the peak power of emissions happen at different wavelengths. So this is T1, this is T2, this is T3. T3 will be greater than, T2 will be greater than T1. So this is lambda m, this is T1, okay, lambda m1, this is lambda m2, this is lambda m3. What is this lambda m? Lambda m is the wavelength at which the EB lambda is maximum. Lambda m is the wavelength at which the EB lambda is maximum at a given temperature of the body. As observing, as the absolute temperature of the black body is increasing, all temperatures, remember, when you are doing the radiation problems, precaution that all temperatures must be in Kelvin scale, 273 plus Celsius. Okay, no, don't keep any temperature in Celsius. Just like remember when you are using the Carnot theorem problems, Carnot heat engine, Carnot refrigerator problems, Carnot heat pump in thermodynamics, you have to keep only the temperatures in Kelvin. Similar manner, here also all temperatures in Kelvin. So this lambda m1 is the wavelength at which the EB lambda is maximum at a given temperature. As the temperature is increasing, lambda m is decreasing. Lambda m is inversely proportional to the absolute temperature. This product is a constant. This is famously known as Wien's displacement law. This is asked once in a GATE. Wien's displacement law. T3 greater than T2 greater than T1. See, same black body at 3 different temperatures, the EB lambda variation is shown. So remember this particular graph and regarding the Wien's displacement law. This product is 2898 micron Kelvin. This is famously known as Wien's displacement law. Solar, you remember this value also. Solar radiation is a black body radiation. Sun is considered as a black body. Remember, best example for the black body is sun, and you may take ice also. Ice and sun both can be considered as a black bodies. Okay, and above all, the most important law is Stefan-Boltzmann law. The total hemispherical emissive power of the black body is given by sigma T to the power of 4. Remember, this is a Stefan-Boltzmann constant. They will give 5.67 into 10 power minus 8 watt per meter square Kelvin to the power of 4. You remember this Stefan-Boltzmann constant. Okay, and for a non-black body also we can calculate. For a non-black body, epsilon into EB we may consider it as sigma T to the power of 4. T should be in Kelvin only. Remember, T has to be kept in Kelvin only. So these are the main laws. Actually, one more law is also there, Lambert's cosine law. I is equal to I n cos theta. That is not that important. That is for a diffuse surface. Lambert's cosine law. Totally 5 laws are there. Kirchhoff's law, Planck's law, Wien's displacement law, Stefan-Boltzmann law, and Lambert's cosine law. Lambert's cosine law is not that important in the gate point of view. I is equal to I n cos theta, where I n is the normal intensity of radiation. A diffuse surface will have the same intensity of radiation along all the directions. A diffuse surface is that body where the intensity of radiation is independent of the direction. Grey body is that body for which the monochromatic emissivity is independent of the wavelength. Okay, I repeat once again, a diffuse surface is that surface for which the intensity of radiation is independent of the direction. Grey body is that body for which monochromatic emissivity epsilon lambda is independent of the wavelength. Most of the gate problems, almost all the radiation problems, we assume that surfaces are diffuse and as well as grey. If the body is black, by default it is diffuse. Black body has 3 characters: perfect absorber, ideal emitter, and diffusive in nature. Please remember these points. And coming to the very important topic, and without this generally gate paper will not come. Shape factor or view factor or configuration factor. Okay, whenever you are doing the shape factor problem, practice, even in the last minute it may help you. Shape factor, also known as configuration factor, also known as view factor. So it is a fraction of radiation energy leaving one surface that could be reaching the other surface. Okay, what is a shape factor means? Fraction of radiation, F12 means fraction of radiation energy leaving the surface 1 that can strike upon the surface 2, that can reach upon the surface 2. After reaching, what will happen? Shape factor, don't bother. So whenever you are doing the shape factor problems, most important thing is reciprocity relation. Reciprocity relation. A1 F12 is equal to A2 F21. A1 F12 is A2 F2. That what is the use of this? If you know one shape factor, you can immediately calculate the other one by knowing the areas. Actually, whenever you are doing the shape factor problems, which is most likely to be asked in the GATE examination, you see there are so many problems asked about the shape factor in all these last 25 years of GATE, many times. So, precaution regarding the problems of shape factor is number. You have to cleverly number. If the number is given in the problem, yes, cleverly follow that. What is the number given to each shape, each geometry, what is the area of that, carefully observe that. Then the problem becomes very easy. I just do a problem there. For example, there is a circular plate on which a hemispherical dome is there. Hemispherical dome, hemisphere. This is a circular plate, radius is r. If you can number this as 1, you can number the inside surface as 2. Sometimes some GATE problems you will number this as 1, you will number this as 2. You will try to mischievously that you would like to drag you to other direction. You may give you number 1 and number 2. So what is number 1, what is number 2, you have to remember. And one more thing, whenever a surface is completely surrounded by other, here very clearly I can say, here I can clearly say F12 is 1. So by using that formula, F21 is A1 by A2. What is A1? Pi r square. A2 is 2 pi r square, hemisphere area. It is 1 by 2. F21 is 1 by 2. So you can quickly calculate the other shape factor. Remember this formula. And very commonly as asked, very long cylinders, infinitely long concentric cylinders. In the side view you may see like this. This is asked many times in GATE, this case. You have to number this as 1, this as 2. For very here F12 is 1. You can see this is 1. This is sometimes you may number this as 2 and this as 1. So F12 is 1. Therefore A1 F12 is equal to A2 F21. F21 is equal to A1 by A2. For a length of L, pi d1 L, this is d1 by d2. Okay. F22, say for example F22 is there, F22 will be 1 minus F21, that is 1 minus d1 by, because the energy leaving 2, the radiation energy leaving 2 cannot go anywhere else, it has to fall on the 1, the energy leaving 2, it cannot go anywhere else. Some portion of that can reach the 1, all that balance portion should have to go to the 2, neglecting the end effects, because they are infinitely long cylinders. If they are finite in length, it is a different situation. If it is infinitely long cylinders, yes, these are the F12, F21, F22. This is asked many times in GATE, okay. And geometry, you have to, shape factor is a geometrical factor. Okay, in one GATE question, he has asked two plates of the same dimensions just kept at an angle of 20 degrees. Shape factor can never be maximum. This is a less than or equal to 1. Shape factor cannot be less than 0, cannot be more than 1. He has asked two plates and kept at an angle of 20 degrees. What would be the approximate shape factor? He has given two options greater than 1. Shape factor can never be greater than 1. By seeing that, I can say F12 will be somewhere around 0.86, 0.85. By seeing the options, I can say. Actual formula is there, 1 minus sin alpha by 2. Some formula we have to remember. Two plates of which are extending by this length and is equal to this length, extending indefinitely in other dimensions, indefinitely in other dimension, and but they are this length and this length are same. What is the F12 value? Questions of this sort are, and otherwise spheres. Say for example, two spheres are there. Sphere R1, R2. Spheres, concentric spheres. F12 is clearly 1 because if this is 1, this is 2. F21 will be A1 by A2. What is A1? 4 pi r1 square, this is r1 square by r2 square. Such kind of questions, simple questions only. But in another gate he has asked one hemispherical dome and this is kept on spherical body. But the 2 is considered closed one. The entire thing is taken as 2, whole thing, this hemisphere and base, but this is the sphere, this is the spherical ball. Then what is the F2? So what you have to do? F12 is 1, no doubt. What is F21? A1 by A2. But when you talk about A2, what are the area of A2 you have to consider? We have to consider this hemisphere area plus this circular base area. When you talk about A2, we have to consider the hemispherical area plus the circular base area. A1 is obviously the area of that spherical ball. We can calculate F21 and you can calculate F22 also. What is F22? 1 minus F21. In another gate he has asked a spherical container is having a cylindrical body, solid cylinder, a solid cylinder. So this is sometimes this may be 1, this may be 2. F21 is 1 here. F12 is equal to A2 by A1. When you talk about the A2, what is the area there? Cylinder area plus this circular area also we have to consider because it is a solid cylinder. It is a solid cylinder. We have to consider this cylindrical surface area plus and 2 circular areas. So give an extra attention in these 8 days. More focus on the shape factor. Most likely to be asked. And coming to this another now until now definitions and shape factor and laws. Now if you want to calculate radiation heat exchange between two infinitely large planes, this case was also many times asked. What is the net radiation heat flux? Net radiation heat exchange. Flux means per unit area. When you are talking about infinitely large planes, by default we calculate the heat transfer rate per unit area. Flux, heat transfer rate per unit area. Remember this formula. Sigma emissivity are given 1 by epsilon 1 plus 1 by epsilon 2 minus 1. This is epsilon 1 will be given, epsilon 2 will be given, T1, T2. We can calculate the net radiation heat flux. Net radiation heat exchange means how much one is giving to the 2, how much one is getting from the 2. The difference, how much one is giving to the 2 minus how much one is getting from the 2. That difference is called as the simultaneously radiation heat exchange is a two-way phenomenon. One will be giving the energy to the 2. At the same time, one is also receiving the energy from the 2. How much it is giving to the 2, how much it is receiving. The difference is called as the net radiation heat exchange. So please remember this formula. Very often the questions are asked on this. And another important case you have to remember is, this is a very important case. Two infinitely long cylinders, this is 1, this is 2. What is the net? Here no flux, it is not per unit area. This formula also remember, sigma T1 power 4 minus T to the power of 4 into A1. Here we don't calculate flux. A1 by A2 into 1 by epsilon 2 minus 1, so many watts. This formula is, you can write for so many cases whenever one shape factor is 1 and other shape factor is less than 1. Whenever you want to write this formula, the conditions are that one shape factor should be 1 and other shape factor should be less than 1. Only 2 surfaces should be there. And another thing is, precaution is always number the inner surface as 1 and outer surface as 2. Always the inner as 1, inner surface is 1 and outer surface is 2. Then only this formula is valid. Okay. And that means 1 is completely surrounded by 2. Under this condition, yes, we could write this formula. Like for example, I give this example. One circular floor is completely surrounded by hemisphere. Here F12 is 1, F21 is less than 1. Yes, we could write that formula. But what is being enclosed is 1, what is enclosing is 2. Outer surface is 2, what is being enclosed, we should number it as a 1. So now with this condition, we can write that previous formula. We don't have to bother whether T1 is more or T2 is more. Don't try to change the formula. Never try to change the formula. T1, sometimes T1 may be more or T2 may be more. Supposing if T2 is more than T1, you will get a negative answer. When you get a negative answer, we mean to say that net heat transfer is from 2 to 1. Okay, supposing if T2 is more and T1 is lesser, don't change the formula. The formula remains the same, but if T2 is more than T1, you will get a minus answer. Minus answer indicates that net radiation heat transfer is from the surface 2 to the surface 1 because T2 is greater than T1. Because radiation heat transfer also obeys the Clausius statement of the second law of thermodynamics. Net heat transfer is always from higher temperature to the lower temperature. Radiation heat transfer also obeys the Clausius statement of the second law. What is that second law says? Second law of thermodynamics, Clausius statement of second law of thermodynamics. Heat transfer always occurs from high temperature to the low temperature. So radiation also obeys that. So what I mean to say is, whether T1 is more or T2 is more, don't bother. To write this formula, only one condition is that F12 should be 1 and F21 must be less than 1. Numbering the surface, inner surface is 1 and outer surface as 2. You can blindly write this formula. Only 2 surfaces must be there. The inner surface should be numbered as 1, outer surface should be numbered as 2. Which is higher temperature, which is lesser, don't bother. You can blindly write this formula, you will get the answer. If you get a minus answer means T2 may be greater than T1. That conclusion, you can, by reading the problem, you can easily notice that. Okay, this is very important formula for calculating the radiation heat transfer between two surfaces. Suppose if I say, for example, here I am giving one special case. Suppose A1 is far lesser than A2, then this will become 0. A1 by A2 tends to 0. So all this will vanish, only epsilon 1 will go to the numerator. Problem becomes even simpler. That can be used, supposing one plate is there, maybe 1 meter by 1 meter plate. If it is kept in a outer ambient is taken as a surface 2, entire ambient is 2, this plate is 1. Okay, the plate, though it is 1 meter by 1 meter dimension, it may be small as compared to the very large surroundings. Yes, you can write this formula. Supposing a plate is there, a plate 1 meter by 1 meter, surroundings are there, large surroundings, entire surroundings is 2, this is 1, A1 by A2 almost tends to 0 because surroundings are very large, though it is and you can use that formula, case 2 formula I had given. Okay. And when you talk about the radiation networks, how to construct the radiation networks, that is very important. Network technology, radiation network technique is very useful to solve the radiation heat exchange when there are 3 surfaces are there, 4 surfaces are there, 3 are there, 2 are there, anything, 2 are there, any number we can, it is a general technique where we define 2 resistances which are called as the surface resistance and space resistance. Surface resistance is given by 1 minus epsilon E by epsilon into A. This is 1 upon A1 F12. This resistance will be there at every surface. Supposing there are 3 surfaces are there, one surface here, another surface here, and another surface is there. 3 surfaces are exchanging heat by radiation, only 3 are there. This technique says that on every surface, here, keep the surface resistance. On every surface, one surface resistance, you paste it. Between any 2 surfaces, between these 2 or between these 2 or between these 2, the space resistance is there. Why it is called space resistance? This resistance will exist in the space. This resistance will exist in the space. Between any 2 surfaces, we keep one space resistance. On every surface, you keep one surface resistance. Supposing if he is asked to calculate what is the net radiation heat transfer between 2 and 3, he is not bothering about 1. What is the net radiation heat transfer between 2 and 3? What do you have to do? Draw the radiation network and then try to calculate the current, radiation heat transfer current, passing through the space resistance existing between 2 and 3. Passing through the space resistance existing between 2 and 3. Then that will give the net radiation heat transfer between 2 and 3. Radiation network technique is very useful. Asked 2 or 3 times, 3 to 4 times in previous gates. Okay, in one of the gate examination is asked 2 plates are there and surroundings are there. He has given all the temperatures, emissivities, etc. etc. Some are black. And what is the net heat transfer between 2 and 3 as well? Surroundings are very large. I can put it as the 3. If they are black, if one is black, this is black. 2 is also black. For black body, there is no surface resistance. Why there is no surface resistance for the black body? Emissivity of the black body is 1. Therefore, this will become 0. The surface resistance of the black body is 0. So, when you construct the radiation network, how many, actual general network I am considering. This is this for a 3 body, this is the radiation network. This is the surface resistance of 1 minus epsilon 1 by epsilon 1 A1. This is 1 minus epsilon 2 by epsilon 2 A2. This is 1 minus epsilon 3 by epsilon 3 A3. Each one will have surface resistance. What are the terminals for the surface resistance? EB1, J1. This is EB2, J2. What is J? Radiosity. This is EB3, J3. So, for the surface resistance, the terminals are EB and J. For the space resistance, the terminals are J1, J2 or J2, J3. The radiosities are the terminals for the space resistance. The terminals for the surface resistance are EB and J. Now we can construct the radiation network. See, this is a general radiation network for 3 bodies, 1, 2 and 3. Luckily, if the body 1 is black, this will become 0. If the body 1 is black, emissivity of the black body is 1, this will become 0. Body 2 is black, this resistance will become 0. EB3 is there, but this resistance also may become 0 if A3 is A3 tends to infinity. Why A3 tends to infinity? Surroundings are very large. This also may become 0. So, what is the final network? Final network become like this. All the surface resistances have become 0. Therefore, EB1 has become equal to the J1. When this resistance has become 0, EB1 has become equal to the J1. EB2 has become equal to the J2. Okay. And EB3 has become equal to the J3. Only 3 resistance. And this current will give the Q122 net. This current may be given the Q123 net radiation heat transfer. This current will give the Q223 net radiation heat transfer. Assuming that surroundings are at the lowest temperature. Okay, 1 is higher, 2 is lesser, 3 is the least. So, that is how we can make use of the radiation network method. Radiation network method is very useful because by using that radiation network technique, we can calculate the net radiation heat transfer between any 2 surfaces, even if there are 3 are there, 4 are there, any number of surfaces. It's a general procedure, general technique. Only precaution is we have to, on every surface, we have to keep one surface resistance. Between any 2 surfaces, we have to keep one space resistance. Here, one is simultaneously exchanging heat with 2 and 3. Okay. 3 is simultaneously exchanging heat with 2 and 1. Okay, like that. So, this is the general radiation network for three body surfaces. Three surfaces are there which are exchanging heat among themselves. Why these surface resistances have become 0? For black body. For black body surface resistance is 0. Okay. If the surface is very large like surroundings, then also the surface resistance is 0. See, when A3 is infinity, this resistance will vanish. And the required current, supposing this current we need to calculate net radiation heat transfer between 2 and 3. That means we have to calculate this heat current, for which you have to know EB2 and EB3 and what is this resistance. First let me keep this 1 upon A1 F12. This resistance is 1 upon A1 F13. This resistance is 1 upon A2 F23. Only thing is shape factors we have to calculate and solve the problem. Areas will be anyhow given in the problem. This model was asked 2 to 3 times in the gate. Okay. So learn the radiation network, revise the radiation network, and you can solve most of the problems of radiation. Okay. So and particular another important thing is shieldings. So you see important things, the questions being asked, the shields, radiation shield will be there. When radiation shield is there, this has surface resistance, this has, there is a space resistance, this has surface resistance, this has surface, there is a space, there is a surface resistance. So there are 4 surface resistances, 1, 2, 3, 4 and 2 space resistances, all are connected in series. This is the radiation shields. That is an important model which was asked in a gate. And okay, this is surface resistance, there is a surface resistance, there is a surface resistance, there is a surface resistance. Okay. And there is a space, there is a space resistance, there is a space resistance here. So all are connected in series. 4 surface resistances and 2 space resistances, everything is connected in series. We can easily calculate, you can number this as 1, this as 2 and shield. Shield will have 2 emissivities, both sides. Sometimes they may be equal or may be unequal. This is epsilon 1, this is epsilon 2. Construct the radiation network. Okay, all resistances put up in series. What is the space resistance here? 1 upon A1 F13. What is the space resistance here? 1 upon A3 F32. Okay. And here Q with the important formula, remember, Q with N shields will be 1 by N plus 1, Q without any shield. You remember this particular condition also. If only if all emissivities are same, all epsilons are same. When all epsilons are same, this rule is applicable. That means if you want to reduce the heat transfer rate by 50%, how many shield you have to keep? 1 shield. 1 shield if you keep, provided all emissivities are equal, if you keep 1 shield, heat transfer rate will exactly reduce by 50%. If you want to reduce the heat transfer rate by 75%, how many shields you have to keep? You have to keep the 3 shields. That means 1/4 means what? It has become 25%. 75% reduction is there. If you keep 3 shields, heat transfer rate reduction will be 75%. Conditions apply only if all the emissivities of the shields, surfaces, everything are equal. This rule is valid. Remember this particular, revise this case also quickly. Coming to the convection. I don't know why many students throughout my experience, convection means tougher, we want to leave that. Never leave. Convection is the easiest topic. But we have to wisely attack the convection problem. First thing is, decide whether it is a forced or free. How do you decide? I am telling the algorithm. Forced or free. Forced or free means if the velocity is given, wind velocity is given, flow rate is given, mass flow rate is given, it should be a forced convection. If no velocity, nothing is given, still air means stagnant, still fluid, quiescent medium or still medium means free convection. But questions on free convection only 3 or 4 times only they were asked. Most of the gate problems asked about the forced convection only. Velocity will be given. Clearly you will read the velocity or otherwise mass flow rate. Anyhow, mass flow rate is equal to, we know that rho AB from the continuity equation. If you are thorough with the boundary layer theory in the fluid mechanics, and if you are thorough the incompressible flow through pipes in fluid mechanics, because those two chapters, if you thoroughly prepare in FM, one shot, two boards, the FM will become easy. Here also convection chapter also becomes easy. Theory of boundary layer, where you calculate hydrodynamic boundary layer thickness, local Reynolds number, etc. And also the incompressible flow through pipes, where you classify the flows as laminar, turbulent, Reynolds number, etc. Again, those two chapters are essential for understanding the convection. So, as far as the convection chapter is concerned, FM and heat transfer both will merge, because convection is after all heat transfer between a solid and a fluid. If the fluid is having velocity or moving in motion, it is a forced convection. That may be evident by in the form of the mass flow rate or maybe in the form of the velocity directly given in the problem. So, in the forced convection, two situations usually arise: flow over flat plates and flow through pipes. Pipes and ducts both mean the same. Duct internal flows, which are also called as internal flows. Pipes are ducts. Duct means non-circular cross section, it is a duct. If the cross section is a circular, it is called as a pipe. It is internal flows, this is an external flow. That is first, as you read the problem, first decide whether you are dealing with an internal flow or external flow. Then if it is an internal flow, when you talk about the flow over flat plates, a flat plate may be given of known length, a fluid with all the thermophysical properties, the viscosity, conductivity, density, specific heat, everything will be given. Four properties: viscosity of the fluid. See, in the convection problems, the properties of the fluid only are important and will be given. Properties of the solid we don't require. We don't want also. Only fluid properties are required. What are the four properties you given? Rho, mu, Cp, K. Four. They will be given in the problem. There will be a growth of the boundary layer, hydrodynamic boundary layer, whose thickness can be calculated, can be denoted as delta. Hydrodynamic boundary layer thickness delta. Delta is a always normal direction is y, along the plate it is x. Here x is equal to 0, it is called leading edge. Here x is equal to L, it is called as a trailing edge. Then what is the question that most likely to be asked? And most of the questions will be asked about the local convection heat transfer coefficient Hx. And another questions they may be asked about the three dimensionless numbers. When you talk about the forced convection heat transfer problems, the three important dimensionless numbers we define: Reynolds number, inertia force by viscous force. Most important number is Prandtl number, a property, kinematic viscosity divided by thermal diffusivity, nu by alpha, mu Cp by K formula. Alpha is the thermal diffusivity, nu is the kinematic viscosity. Questions on when you talk about the forced convection problems, at least 15 to 20 times you would have seen the problems of questions on Prandtl number. Why Prandtl number is so important is, it is the only dimensionless number which is a property of the fluid. No other dimensionless number, no other number is a property. Prandtl number is the only dimensionless number which is a property. Why? Because kinematic viscosity is a property of the fluid and the thermal diffusivity is a property of the fluid. It is dimensionless. But while calculating Prandtl number, precaution is always keep Cp in joule per kg Kelvin, keep the mu in Pascal second only. Obviously K will be in watt per meter Kelvin. Prandtl number of air is 0.7. Prandtl number of water is around 2 to 6. Remember, at least for air and water. For mercury, Prandtl number will be very, very low, because for mu Cp by K, K is very high for the mercury. Therefore, Prandtl number is very low for the liquid metals. They are called as the liquid metals, mercury, bismuth, etc. For them, Prandtl number is very low. For air, 0.7 you can take, 0.69 or 0.7. So this is another number what we talk about is the Nusselt number. It is the HD by K or HL by K. Actually, when you talk about the plate, it is characteristic dimension is length. When you talk about the pipe flows, characteristic dimension is the diameter. HL by K for flow or flat plates or internal flows, it is HD by K. Nusselt number is also called as the dimensionless temperature gradient. Dimensionless temperature gradient. The other name of the Nusselt number is dimensionless temperature gradient. Okay, HD by K or HL by K. Prandtl number is KV by TD. Okay. Nusselt number would always be also be given like this. Nusselt number is equal to HD by K D by Ka divided by 1 upon HA. So this resembles conduction thermal resistance offered by the fluid if it were stationary. Conduction thermal resistance. Nusselt number questions are very common in GATE. Offered by fluid if it were stationary. Divided by surface convective resistance. Surface convective. So this is the definition for the Nusselt number. Nusselt number is always greater than 1. It is also known as the dimensionless temperature gradient. Okay. So if you know the Nusselt number, the problem of the convection is, because in every convection problem, our main focus will be to calculate the H. Our main intention, our main objective is to calculate the H. Once we calculate the H, we can calculate the heat transfer rate by using Q is equal to HA delta T. So getting that H is all about the Nusselt number. Okay, we got the NU means H is calculated because D is given in the problem, K is given. Okay, for flow or flat plates, again, actually I am telling you the algorithm there. In the forced convection problems, first step is calculate Reynolds number. Calculate Reynolds number, RE. After getting Reynolds number, if for flow or flat plates, if REX is less than 5 lakhs, you can treat the entire flow as laminar for flow or flat plates. For flow or flat. Okay. If it is greater than 7 lakhs, flow would be turbulent. If the flow is laminar, the local Nusselt number is given by this formula. That is, local Nusselt number is given by Hx into x by k. This, whenever you are given a suffix x, it means a local. This means the local Nusselt number. Okay. And generally, when you talk about the flow or flat plates, this is y, this is x. Heat transfer is taking place in this direction. Okay. Heat transfer is taking place in this direction. So there is one particular, in fact, this is the HBL. Then if there is another boundary layer simultaneously formed during the heat transfer, that is called as the thermal boundary layer. The link between hydrodynamic boundary layer and thermal boundary layer is given by the number called Prandtl number. Why the questions on Prandtl number are very common is, most of the questions asked in the forced convection, they revolve around the Prandtl number, because Prandtl number is the property of the fluid which links the hydrodynamic boundary layer with the thermal boundary layer. The relation between delta and delta T, the link between delta and delta T is given by the Prandtl number. Prandtl number, there are three things there. Prandtl number connects delta and delta T. What is the delta T? Thickness of the thermal boundary layer. If the Prandtl number is greater than 1, we can say, if Prandtl number is greater than 1, implies nu will be greater than alpha, implies delta will be greater than delta T. If the Prandtl number is less than 1, kinematic viscosity will be lesser than alpha, that means delta will be lesser than delta. If Prandtl number is equal to 1, delta will be almost equal to the delta. Both the thicknesses will almost be equal. Okay. So, just by seeing the Prandtl number value, you would be able to immediately tell whether HBl is thicker or TBl is thicker. That is an important point we have to remember in the flow over flat plates. And most of the flow over flat plate cases, will be laminar flows only will be asked. Supposing if you want to, for flow over flat plates, average Nusselt number, when you could keep 0.66 bar REL to the power of half, Prandtl number to the power of 100. What is REL? V infinity L rho by mu. Prandtl number anyhow a property. Earlier I had given you one more relation, local Reynolds number. Here REX means what? Local Reynolds number given by local Reynolds at a particular location, V infinity into x rho by mu. This is a local Reynolds number. Prandtl number anyhow a property. You don't have any meaning of local. You will have a local Nusselt number, you have a local Reynolds number, but don't say local Prandtl number, because Prandtl number is a property of the fluid. Okay. This is local Reynolds number, and this is the average. The average means for the entire plate. Incidentally, the average Nusselt number will be equal to the twice the local Nusselt number at x is equal to L, that is at the trailing edge. Similarly, the average convection heat transfer coefficient will be equal to the twice the local convection heat transfer coefficient at the trailing edge. What is NU bar? Average convection heat, bar means average for the entire plate, one single value, H bar L by K. So, these are the things that you need to remember. Generally, if you want to calculate the average Nusselt number, use this formula. If you want to calculate the local Nusselt number, this 0.3, exactly one is a double that, 0.332 and there 0.664. We can see from these relations also. Average convection heat transfer coefficient is twice the local convection heat transfer coefficient at the trailing edge. Okay. This is about the, generally when you talk about the flow or flat plates, 99% cases you will be asked about the laminar flows, because if you want to turbulent flow, if you want to look at that, there will be a formula for the turbulent flow, but the velocities of the winds must be sufficiently high, because for the flow to be turbulent, the local Reynolds number must be more than 7 lakhs or 6.5 lakhs. Generally it won't happen. So, most of the gate problems will be asked about the laminar flows for flow or flat plates. But when you come to the flow through pipes, it is a different situation. For flow through pipes, if it is a duct, supposing if it is a duct, in one of the gate is asked, I think gate 2004, here the characteristic dimension is 4 into cross sectional area by perimeter. This is the perimeter. This is the perimeter, this dimension. Cross sectional is, supposing this is A, this is B, 4 into A into B divided by 2 into A plus B. A plus B will be the perimeter, like that. You have to calculate the characteristic dimension. If Reynolds number, how do you calculate Reynolds number? BD rho by mu is less than 2000, you brand it as the laminar. If Reynolds number is greater than 4000, you brand it as the turbulent flow. Here any chance may be possible, flow may be laminar, flow may be turbulent, but in flow or flat plates, mostly the flows will be laminar. In the gate point of view I am talking. Here you may be laminar, you may get, or generally a viscous oil is flowing in a small diameter pipe. Definitely flow will be laminar, because Reynolds number is less than 2000. If air is flowing in a pipe, by default it will be turbulent flow. Air is flowing with a good velocity. Definitely any gas flowing with a good velocity, the flow would be turbulent. Okay, if laminar flow, the Nusselt number has got two different 4.36 for constant heat flux Nusselt number is equal to 3.66 for constant wall temperature. Two different situations will come here for constant wall temperature conditions. Two different situations you may see in forced convection, particularly flow through pipes, constant heat flux conditions and that is constant wall temperature conditions. Okay. For laminar flow, two different. For turbulent flow, laminar flow means what? Reynolds number is less than 2000. For turbulent flow, only one equation. For turbulent flow through pipe or duct, whatever it is. Only thing is for pipe, the characteristic dimension is diameter. For the duct, it is 4A by P. Nusselt number is calculated from this very famous equation called as the Dittus-Boelter equation or McAdams equation. Dittus-Boelter or McAdams equation. N is equal to 0.4 for heating, N is equal to 0.3 for heating of fluid, N is equal to 0.3 for Nusselt number is. Here there is no business of local and average. The local Nusselt number, average Nusselt number you will see only in case of the flow over flat plates. For pipe flows, for duct flows, you don't see any local or average. You get only one Nusselt number, that is a HD by K, one H, and from which you can calculate the H, convection heat transfer coefficient. Okay, this is for the turbulent flow. If the Reynolds number is greater than 4000. Generally, in the recent gate examinations, particularly 2019, 2019, 20, 21, he is asking the constant heat flux. Generally, when you talk about the constant heat flux conditions, a pipe will be there on which an electrical heating coil is wound all along the length of the pipe, where you are supplying the constant heat flux, so and so watt per meter square. What is the total heat transfer rate between the fluid and the pipe? In such case, total heat transfer rate is nothing but heat flux, Q double dash means heat flux into area of heat transfer. Okay, flux means heat transfer rate per unit area. What is the area of heat transfer? Pi d into L, where L is the length of the pipe. Okay, so many watts. This should be double lines will indicate heat transfer rate per unit area. Between pipe and fluid, total heat transfer rate is obtained. This should be equal to the most important parameter in the forced convection heat transfer in flow through pipes is the bulk mean temperature. Bulk mean temperature. That keeps changing. Bulk mean temperature means the average temperature at a particular cross section. At a particular cross section, what is the mean temperature of the fluid at a particular given cross section? That is called as the bulk mean temperature, which keeps changing. This is TB inlet. Here it is the TB bulk mean temperature at the exit. In any case of the forced convection heat transfer, remember, in any case of forced convection heat transfer in flow through pipes, the total heat transfer rate between the pipe and fluid can be calculated from this formula: mass flow rate of the fluid into specific heat of the fluid into TB exit minus TB inlet. Remember that this formula is valid for any case of flow through pipes, whether a constant heat flux, constant wall temperature, whatever it is. Total heat transfer rate is equal to mass flow rate into Cp into TB exit minus TB inlet. But if it is a constant heat flux, means this flux is constant, right? You are supplying the same heat flux at every location. In such case, the total heat transfer is obtained by multiplying the constant heat flux with the area of the heat transfer. Don't use this formula for a constant wall temperature conditions. Okay, and for constant wall temperature conditions, first let me compare this constant heat flux and constant wall temperature. Constant heat flux means you are supplying the same heat flux all along the length of the pipe, all along the length. In such case, the variation of the bulk mean temperature versus length of the pipe, this is the pipe wall temperature, this is the TW is the pipe wall temperature, bulk mean temperature is the temperature of the fluid. This is pipe wall temperature variation, this is the bulk mean temperature. For fully developed flow, fully developed flow means your temperature profiles are not changing in the direction of the x. Velocity profile is not changing with respect to the x means that is a hydrodynamically fully developed. Thermally fully developed means your temperature profiles along the length of the pipe are not changing. So this is the variation, both are linear very straight lines. Okay. For a constant pipe wall temperature situations, this is another one. There is a flow through pipes there. Constant wall temperature is called. That is a constant heat flux. This is the constant heat flux. Same heat flux you are supplying all along the length of the pipe. This is the constant wall temperature conditions which is obtained by condensing steam. By condensing the steam we can obtain this. The wall temperature is maintained constant. Here see, here the wall temperature is increasing linearly. This is x direction. The bulk mean temperature of the fluid will change like exponentially it will increase. This is the for the bulk mean temperature. But remember here in constant heat flux conditions, the temperature difference between the pipe wall and the TW minus TB, which is called delta T, it is not a function of x. It won't change with x. For a fully developed flow, for a developing flow, it may change. This is a developing flow. This is the developing flow. In one of the gate questions he has asked, it is a developing flow. This is fully developed flow. Once the flow gets fully developed, the wall temperature changes linearly, the bulk mean temperature also changes linearly. The difference will not change with x. At every location, you will see the same difference. But here, the delta T, that changes with x. Delta T, it is a function of x. Here heat flux also is a function of x. Here only wall temperature, see what the wall temperature will be increasing, but heat flux is maintained constant. This is a constant heat flux. This situation is constant pipe wall temperature. Two different situations will arise, but for both the situations, we could write that total heat transfer rate for both the situations, total heat transfer rate between entire pipe and the fluid is mass flow rate of the fluid into specific heat of the fluid and the change in bulk mean temperature from inlet to exit. For any situation, for both the situations. And the gate questions what is asking is, you will give you the constant heat flux. You will give the constant heat flux situation. You will give what will be the heat flux also you will give. He will give you the data. The data also will be given. But he will ask you to calculate what will be the pipe wall temperature at the exit. Here at this situation, TW at exit, how much he will ask. How to calculate that? Now how to do that problem? Heat flux into pi dl is equal to mass flow rate of the fluid into Cp of the fluid into Tb exit minus Tb inlet. Bulk mean temperature. Bulk mean temperature is the bulk mean temperature of the fluid, from which we can calculate first you get the Tb exit. We can calculate the Tb exit from this equation. Tb exit, because Tb inlet will be given always. TB inlet will be given, bulk mean temperature at the inlet will be given, we will be calculating the bulk mean temperature at the exit. After that, because once he gives the local, so whenever there is a constant heat flux conditions are given in forced convection heat transfer in flow through pipes, how would you generally judge it? In the case of the constant heat flux conditions, you will be given an electrical coil wound all along the length of the pipe. So constant heat flux conditions will be achieved by heating the water or the fluid inside the pipe by winding the electric power carrying coil. So that is the indication that it is a constant heat flux condition. Constant heat flux means all along the length of the pipe you will be supplying the same heat flux. Constant means constant in the direction of the flow at every location. This is the flow. Okay. Now, in the case of the constant heat flux conditions, the total heat transfer rate can be calculated by multiplying the heat flux value with the area of heat transfer, which is given by pi dl. So, in any situation of the forced convection heat transfer in flow through pipes, the total heat transfer rate can be calculated by this. So, this is used whether a constant heat flux conditions or a constant wall temperature conditions. The rate of change of enthalpy, in the thermodynamic sense I can tell that it is the rate of change of enthalpy of the fluid from inlet to the exit. So, by using this we can calculate the TB exit. TB inlet by default it will be given, we can calculate the bulk mean temperature of the fluid at the exit. TB means bulk mean temperature. So, at exit if you write the Newton's law of cooling, then if you write the Newton's law of cooling at the exit, just at the exit here, you know the heat flux, heat flux is equal to local convection heat transfer coefficient, which is again mentioned, flux HA delta T I am writing. So, heat transfer rate is taking place between the pipe and the fluid. At the exit, if you write the Newton's law of cooling, heat flux is equal to Hx. What is that Hx? Local convection heat transfer coefficient. Mind that in every forced convection heat transfer in flow through pipes, the local convection heat transfer coefficient will not change in the direction of the flow for fully developed flow through pipes, both hydrodynamically and thermally. For thermally and hydrodynamically fully developed flow through pipes, the local convection heat transfer coefficient is independent of the x. In the direction of the flow, Hx remains constant. But in the developing flow, it may change. But in the fully developed flow, the Hx will not change and the Nusselt number also will not change in the direction of the flow. It remains constant at every location. Hx, if the Hx is given, the local convection heat transfer coefficient is given, I could draw that variation also. Hx versus x. For fully developed flow through pipes, Hx only in the developing flows it will decrease. Once the fully developed flows, it remains constant. X is the direction of the flow. For fully developed flow through pipes, both thermally and hydrodynamically, the Hx remains constant. You can see that Hx value is remaining constant, it is not changing, unlike in case of the flow over flat plates, unlike in case of the external flows. The main difference between the external flows and the internal flows is that in external flows, that is flow over flat plates, Hx will be different at different locations. Hx keeps decreasing in the direction of the flow. Hx will be different at different locations in flow over flat plates, but in flow through pipes and flow through ducts, Hx will be the same at every location in the direction of the flow. Once the flow gets fully developed, both thermally and hydrodynamically. So, if you just write the Newton's law of cooling at the exit, heat flux is equal to Hx into area is 1 because we are dealing with the flux, bulk mean wall temperature at exit. What is the temperature difference between the pipe wall and the fluid? T wall at exit minus bulk mean temperature at exit. We have already calculated bulk mean temperature at exit from this energy balance. This is energy balance or the first law of thermodynamics. The total heat transfer rate is equal to the rate of change of enthalpy of the fluid from inlet to the exit is this, from which I got the TB exit. The TB exit is substituted here in the Newton's law of cooling, from which you can calculate T wall temperature at exit can be obtained. So, this question was asked once or twice in the previous gate examinations. So once again I am telling only 2 steps. You have to obtain the bulk mean temperature at exit by using this energy balance. After obtaining the TB at exit, just write the Newton's law of cooling just at the tip of the pipe, at the exit of the pipe. You know the heat flux given in the problem, Hx also given in the problem. Supposing if the Hx is not there, you may ask, then you have to use the, if you just check it, whether it is a laminar flow or turbulent flow. But the Nusselt number, you know the equations for calculating the Nusselt number. Nusselt number is equal to Hd by K. From that calculate Hx and get that, use that Hx here. We know how to calculate the Hx from the Nusselt number equations. For the laminar flow, we got 2 values of Nusselt number at given, 4.36 for constant heat flux, 3.66 for the constant boil temperature. For turbulent flow, only one equation, that is Dettus-Boelter equation. See, the main difference between the laminar flow and turbulent flow heat transfer is, in the laminar flow, for constant heat flux and constant boil temperature conditions, Nusselt number values are different. Whereas for the turbulent flow through pipes, if the Reynolds number is greater than 4000, Nusselt number value will be the same both for constant heat flux conditions and constant boil temperature conditions. Nusselt number value will be different between constant heat flux and constant boil temperature conditions only in the laminar flow, that is when the Reynolds number is less than 2000. Please remember all these points. Make a short notes just before going to the exam, because we have got 8 days more. Very quick revision you do it. That is the purpose of this video, right? So this is I think you have understood there. This is a difference between the constant wall conditions and constant pipe wall temperature conditions and constant heat flux conditions. So and for flow or flat plates, this question also may be asked. Hx for laminar flow, Hx for laminar flow over flat plates. For laminar flow over flat plates. For flow through pipes, whereas here it is keeps on decreasing, right? For fully developed flow. Fully developed means both thermally and hydrodynamically. Okay, this is the developing flow. So actually problems on convections are quite easy if you just follow the procedure, if you just follow the algorithm. I already said, fix the characteristic dimension. If it is a flat plate, it is the length. If it is a pipe, it is a diameter. If it is a duct, it is 4A by P. Then calculate the Reynolds number. Decide whether the flow is laminar or turbulent, and then choose the appropriate formula for the Nusselt number. Okay. If it is the flow is turbulent flow, in this case, for flow through pipes, this is for fully developed flow through pipes. This is for flow through pipes. Internal flows, I can say. This is for the plates. For flow or the flat plates, it keeps decreasing. Okay. For decide the flow, laminar or turbulent, and then select the equation for calculating the Nusselt number. Okay. In case of the turbulent flow, here there is only one equation, that is Dettus-Boelter equation or Macadam's equation. Nusselt number is equal to 0.023 into Ru to the power of 0.8 into Pr to the power of n. If it is a flow or flat plates, then mostly you expect the laminar flow, I can say. Almost all the gate problems earlier given, most of the cases you will see laminar flows for flow over flat plates. But when you come to the internal flows, the flow can be laminar, flow can be turbulent, any problem you may get. So when you talk about the convection chapter, what are the most likely things you have to focus is Prandtl number, definition of Prandtl number, calculation of Prandtl number, significance of the Prandtl number. What is the physical significance of the Prandtl number? It connects the hydrodynamic boundary layer thickness and thermal boundary layer thickness. Okay, for some generally that for flow or flat plates, this relation also we remember. For laminar flow over flat plates, if you want to calculate the delta T, thermal boundary thickness, delta could be obtained. This is HBl thickness. This is HBl thickness. You can remember this equation is also called as, famously known as, Blasius solution. 5x by root of Rex, where Rex is given by Rex is given by V infinity into x by nu. Nu is a kinematic viscosity. So remember this formula. If you want to obtain the thermal boundary layer thickness at any particular location, first calculate the local Reynolds number, get the hydrodynamic boundary layer thickness, and then calculate the thermal boundary layer thickness at the same x. Mind that actually both will grow for flow or flat plates. Both HBl and TBl directly will form. Okay, this is HBl, this may be TBl. If TBl is thicker at any x, if TBl is thicker than HBl, that means the delta T is greater than delta, this is delta T, whereas this is delta. If delta T is greater than, alpha is greater than nu, implies Prandtl number is less than 1. That is example air. Example air. For air, Prandtl number is less than 0.1. Prandtl number of air is 0.69 or 0.7. So knowing delta, we can obtain delta T. Knowing delta T, you can obtain delta, vice versa. That is the significance of Prandtl number. Most important question you may expect. Then a constant heat flux, constant wall temperature. How do the temperature of the pipe wall will change on the constant heat flux? I already said both pipe wall temperature and bulk mean temperature both will increase linearly, with the difference between them remaining constant with respect to x. Look at the temperature profiles I have drawn. Okay, whereas in the constant pipe wall temperature conditions, the bulk mean temperature of the fluid increases exponentially. So please give a focus on the how the temperatures of the pipe wall and bulk mean temperature of the fluid change in the direction of the flow in both the situations, constant heat flux and constant pipe wall temperature conditions. Now coming to the last and easiest chapter of the heat transfer subject, heat exchangers. This is the easiest chapter. Whenever you are reading the problem, heat exchanger, immediately attempt that. Within 1 minute you can solve that, because there are only two methods of problem solving in heat exchangers. One is LMTD method, another is effectiveness NTU method. So easiest chapter, very easy chapter. Only two methods are there. Any problem of heat exchanger can be solved by using these two methods, effectiveness NTU method. Okay. And actually, when you talk about the LMTD, it is also called as a design of heat exchanger. That is to calculate area A, area of heat exchanger calculation. In the effectiveness method is called as a performance of the heat exchanger. That means what to calculate here, both cold exit and hot exit, both are to be obtained. So this is, if you read three temperatures, if three temperatures are given, if you read three temperatures, then go to this method. If you read only two temperatures, then go to the straight, we can decide. By reading the problem itself, we can decide. If you are because in every heat exchanger there will be four temperatures, THI, TCI, THE, TC. If three are given, go here. If two are given, go there. And what type of heat exchanger is being given, that will be anyhow you will be reading, either a parallel flow or a counter flow. Okay. First, actually parallel flow means that how to draw the temperature profiles, just try to know that, and we know how to calculate that LMTD and try to get the delta Ti and delta Te. It is a parallel flow, it is a counter flow. This is a parallel, this is the counter flow. But the definitions of delta Ti and delta Te are different. Here delta Ti means THI minus TCE. Here delta Te means THE minus TCI. The definitions of delta Ti and delta Te are different. This is a delta Te here. This is the delta T, this is a counterflow. But the formula for the LMTD is same. Delta Ti minus delta Te divided by Ln natural logarithm. You use in the calculator natural logarithm function. Okay. Because log mean temperature difference, you get some answer in Celsius. But the same answer, same in Kelvin, because it is a temperature difference, right? Don't add the 273 here. Temperature difference, whether it is a Celsius or Kelvin, the value is same. So log mean temperature difference 20 degrees Celsius. What is its value in Kelvin? It is 20 Kelvin, right? And on some special cases, remember, some special cases means if m dot h CPH is equal to m dot C CPC, capacity rates are equal in counterflow. This is a one very important case in counterflow heat exchanger. Then only you will see a parallel straight lines. You see, that means delta Ti is equal to delta T. Straight lines there. This is delta Ti is equal to delta Te. Both of them are equal to the LMTD. LMTD is equal to either delta Ti or delta T, anyone. In this a special case, it is also known as balanced counterflow heat exchange. Such situation, balanced counterflow heat exchange. This is a hot fluid. This is a cold fluid. This is one important special case regarding the LMTD. What do you mean by balanced counterflow heat exchanger? If the capacity rates are equal on hot side and cold side. Okay. And remember, for a given heat transfer rate, and for a given mass flow rates of the hot and cold fluids, counterflow heat exchanger occupies always lesser area than the parallel flow, because when all four temperatures are same, comparison, when you see the comparison, when all four temperatures being same, in all the three types of heat exchangers, LMTD of counter is greater than LMTD of cross flow is greater than LMTD of parallel. Parallel is least. Otherwise, area of the counter, here I can say, area of the counter is lesser than the area of the cross flow is lesser than the area of the parallel. Because for any type of heat exchanger, this is the governing equation, right? Q is equal to UA delta Tm. U is the overall heat transfer coefficient, which is equal to the rate of enthalpy change of either hot side fluid or the rate of enthalpy change of cold side fluid. This is the energy balance. This is from the energy balance, the rate of enthalpy change of hot side fluid or the rate of enthalpy change of the cold side fluid from inlet to exit should be equal to the total heat transfer rate between hot and cold fluids in entire heat exchanger. Total heat transfer rate between hot and cold fluids in entire whole total heat exchanger. But one very important thing is this overall heat transfer coefficient, we have to keep it in watt per meter square Kelvin. Therefore, the main precaution in heat transfer subject is always keep the specific heat in joule per kg Kelvin. This is the mass flow rate, always in kg per second. Never keep the specific heats in kilojoule. It will be given in kilojoules, but convert into the joule per kg Kelvin. Because finally we want the answer in watts. And some other special case regarding LMTD is if one of the fluids is undergoing phase change, then LMTD value LMTD is same. LMTD is same for both parallel flow and counter flow. For both parallel flow and counter flow. Example, steam condenser. Best example is steam condenser. In the steam condenser, when the hot steam is condensing, its temperature remains constant. It won't change. Steam, hot THI is equal to THE. But the cold fluid temperature keeps increasing. TCI, TC. So it is a parallel flow. That LMTD value will be the same even for the counter flow. So when one of the fluids is undergoing phase change, it does not matter what type of heat exchanger we are going to design. Whether you design a parallel flow or a counter flow, the area will be the same. In the design of heat exchanger, our main objective is to calculate the area of the heat exchanger, for which we have to calculate first LMTD, and then after calculating LMTD, we have to obtain. First, once you obtain LMTD, U will always be given. Supposing if U is not given, we can use this formula. 1 of the H on the hot side, convection, you can use roughly this cold side, convection coefficient on the hot side and cold side, and without fouling. No fouling here. No fouling. Fouling factor is given, you have to take care of that. Fouling means the uncleanliness, the rust or the scaling, the scale formation, chemical scale formation on the pipe surfaces is called as the fouling. That may reduce this overall heat transfer coefficient. So if without fouling, this, if the H is given, you can calculate overall heat transfer, but coefficient, overall heat transfer coefficient, but mostly the overall heat transfer coefficient will be given. This Q will be obtained either from this or from this. Immediately we can calculate the area. So in the design of heat exchanger, first get the LMTD. So generally if 3 temperatures are given, how to get the LMTD? Because to get the LMTD we require all the 4. We have the energy balance. This energy, if 3 are given, we can calculate the 4th one from this energy balance and then obtain the LMTD and then use this equation, calculate the area. So that is called as the LMTD method. In the other method, in the next method, that is called effectiveness. Effectiveness is Q actual by definitions we have to know. Q maximum possible. This is a effectiveness has got 2 different formulae. TCE minus TCI divided by THI minus TCI if m dot C CPC is lesser than m dot H CPH. Effectiveness has got another formula, THI minus THE divided by THI minus TCI if m dot H is CPH is lesser than, and that means if the capacity rate, this product m dot Cp product is called as capacity rate. M dot Cp product is called as heat capacity rate. If it is lesser on the hot side, you select this formula for the effectiveness. If it is lesser on the cold side, you select, if the capacity rate is lesser on the cold side, you select this formula. If the capacity rates are equal on both hot side and cold side, any formula we can select. Okay. Effectiveness is defined as actual heat transfer rate by maximum possible heat transfer rate. You select this formula for the effectiveness if the capacity rate is smaller on the cold side. You select this formula for the effectiveness if the capacity rate is smaller on the hot side. This product, m dot Cp product, is called as the capacity rate. And number of transfer units, it is given by UA by m dot Cp small. UA by m dot, but U should always keep it in watt per meter square, and the Cp we have to keep it in joule per kg. NTU can be less than 1, can be more than 1, but effectiveness will always be less than 1. But most probably NTU values you should be getting between 1.5, 1.25, 2 like that. If NTU is getting more than 3 or 4, means you have to suspect your question. Somewhere you are going wrong. NTU mostly will be not more than 2.5 or 3. Very commonly you will get 1.5, 1.75, 2 like that. And we have got another dimensionless thing, m dot Cp small by m dot Cp big. C is equal to 0 if one fluid changing phase. One fluid is changing phase, like steam condenser, C will be 0, because for that fluid m dot Cp big becomes infinity. When this is infinity, C will be 0. For in steam condenser, in steam generator, steam condenser, C value is 0. Okay. C can be 1. When the C will be 1, both the fluids have got the equal capacity rates. If m dot H Cph is equal to m dot C Cpc, then obviously C value will be 1. So these three are the three dimensionless parameters in the effectiveness NTU method. Effectiveness is defined as actual heat transfer rate by maximum possible heat transfer rate. Usually effectiveness values will be somewhere between 0.5 to 0.8, usually 0.75, 0.65 like that. NTU values usually it will be 1.25 to 1.25 to 2.5, in that range you will get 1.25, 1.15 like that also, usually 1.15 like that. And C can be 0 if one fluid is undergoing phase change, C can be 1. But if you get the values out of that bound, if the effectiveness is 0.2 or 0.3, somewhere you are going mistake. If the NTU got somewhere around 4.5 or 6 something, you are doing mistake. You can cross check the values. Usually NTU can be less than 1 also. But usually it comes around 1.15, 1.52 like that. And they are related. Effectiveness is a function of NTU comma C. Effectiveness of the parallel effectiveness of the counter will be this is the effectiveness of the counter, the formula, that is the effectiveness of the parallel. If C is equal to 0, effectiveness of the parallel and effectiveness of the counter will be same. Steam condenser, when the C will be 0 in steam condenser, it will be 1 minus e to the power of minus NT if one fluid is undergoing phase change. If C is equal to 1, effectiveness of the counter, it becomes undefined, but it can be obtained from L'Hospital's rule. This is if C is equal to 1 for the counter. For the parallel, 1 minus e to the power of minus 2 into NTU by 2. Some special cases you have to remember. If the C is equal to 0, when one fluid is undergoing phase change, for both parallel flow and counter flow, LMTD values will be the same, effectiveness value will be the same, area will be the same. It does not matter what type of heat exchanger you are going to design. Okay. It doesn't matter what type of heat exchanger you are going to design if one of the fluids is undergoing phase change like in steam condenser. Generally, effectiveness NTU method will be useful to get both the exit temperatures. If you want to calculate, I already said, in the heat exchanger problem, if only you are reading 2 temperatures, totally in any heat exchanger 4 will be there. If you are reading just 2 temperatures, directly go to the effectiveness NTU method. If you are reading 3 temperatures like THI, TCI, THE, only TCE is not there, not given. Yes, of course, we can calculate by using energy balance. In such case, go to the LMTD method. If you are reading 3 temperatures in the heat exchanger problem, go to the LMTD. If you are reading only 2 temperatures, go to the effectiveness NTU method. But both the methods, the purpose is different. LMTD method is meant for area. Effectiveness NTU method is meant for calculating both the exit temperatures. So to get both the exits, to get both exit temperatures, first calculate m dot H Cph and m dot C Cpc. both the capacity rate obtained. Then get the C, m dot Cp small by m dot Cp big, because in the heat exchanger, in any heat exchanger problem, mass flow rate, specific heats by default will be given. But for water it may not be given, but remember that for water we know that 4.186 kilojoule per kg Kelvin. Cp of the air, it is 1.005. 1.005 kilojoule per kg Kelvin. So after getting the C, then get the NTU. U will always be given in every heat exchanger problem. And one more thing I'd like to tell that in the heat exchanger problem, if you are reading area, just go to the NTU method. If you are reading, if the area of the heat exchanger is given in the problem, blindly go to the effectiveness NTU method. If area is not given, if you want to calculate the area, go to the LMTD method. After obtaining NTU, calculate effectiveness, because it is a function of NTU comma C. We already seen the formula. Parallel flow, you got one formula in terms of NTU C. Counter flow, you got a different formula. Get the effectiveness. Then choose the appropriate formula for the effectiveness based upon which side the capacity rate is smaller. Here the precaution must be given. Generally, students will commit mistake here. After calculating the effectiveness, you select this formula or this formula based upon this step 1, first step. In the step 1, we know which is smaller. If m dot C CPC is smaller, you select this. You select this formula. If the m dot H CPH is smaller, you select that formula. Once you get this, supposing if you are selected, calculate only one exit. Calculate only one exit temperature from one of those two formulas selected. Then how to get the other exit? Now you got the energy balance. Get other exit temperature from energy balance equation. From energy balance equation. Get other exit temperature from energy, that is m dot H CPH THI minus, what is energy balance equation? M dot H CPH THI minus THE is equal to m dot C CPC TCE minus TC. From that equation, calculate the other exit. That equation, energy balance, this energy balance equation valid for any type of heat exchanger. This equation m dot C CPC TCEI is valid for any type of heat exchanger. This is a energy balance. First law of thermodynamics. This is also called as energy balance equation or heat balance equation or first law of thermodynamics. Valid for any type, parallel flow, counter flow or cross flow. Sometimes in cross flow, LMTD of the cross flow means when both the fluids are moving at perpendicular direction. It is by using the same 4 temperatures, you will obtain the counter flow multiplied with the F. This F is called as correction factor. It will be close to 0.9 like that, 0.85 or 0.9. It will be given in the problem. If correction factor is given in the heat exchanger problem, it means that you are dealing with the cross flow. Okay. When all 4 temperatures being same, highest LMTD you see in counter, lowest in parallel, cross flow in between. Okay, but when you are doing the problems of heat transfer, first pick up the heat exchanger problem, because that is easy, very easy. Okay. And if you are doing the problem, if you are reading something like a composite wall and all that, calculating the temperatures or a heat flux or the convection coefficient, etc., from the first chapter, conduction, that is also easy, composite slab or a composite cylinder like that. Okay. So there are in each chapter there are certain areas you have to give a more focus. I have discussed all the things and try to revise those areas in this. You got just 8 days left. So in those 8 days, I hope you would be able to quickly revise this heat transfer, where you may expect minimum 7 marks, may go touch up to 9 marks also. Important scoring subject in heat transfer. This is Sekhar from Msigma Gokulam, with an experience of more than 25 years of GATE teaching experience across various cities in India. This is Sekhar. Wish you all the best, my dear students. Good luck for the GATE 2025 examination. All the best.